Okay, here's another example where when you solve for y sub s, you know that you're gonna have unfactorable denominator, and then technically you have to do the complete the square. Okay, similar to example 3, I recommend you watch the video with the example 3 first. Okay, so you can see that. Okay, so you can see that this example is going to be a little bit faster. Okay, however, before we go moving on to solve this, I just want to give you an idea. Okay, when do you know you expect it? When do you should expect that you need to complete the square? Okay, it's based on let's recall the characteristic method. Okay, so you have r squared minus 4r plus 5 equals 0. Right, you do characteristic method. You try to solve for the complementary solution. Okay, then when you do this, if this one is factorable, okay, then you're gonna have a factorable denominator for this one, for the y sub s. Okay, so if they were not factorable, then this one will have something not factorable. Okay, and indeed it's true. If you do this problem, okay, we're gonna do the determinant square root of b squared minus 4ac. For sure that's gonna be negative. Okay, so let's try that quickly. Okay, so b squared negative 4 square minus 4 times 1 times 5, that is square root of 16 minus 20, that is negative 4. There you go. That's technically plus and minus 2i, because this is a complex, right? You're gonna return a complex, right? This one gonna be e a t, right? Technically e actually is the a cosine of bt plus b sine of bt. There you go. Okay, when we have complex, we're gonna have that thing, right? And because the characteristic equation give you something that is complex, that means not factorable, therefore when you solve for y sub s, it's gonna be not factorable, which is this case. All right. Okay, so let's proceed using Laplace, right? Okay, so Laplace. Okay, so first thing first, Laplace both sides. Okay, we know the truth, right? Right, so Laplace term by term. Okay, with the coefficient thrown outside. Okay, so Laplace second derivative give us x squared y sub s minus ds y sub 0. That the first that the initial condition minus another initial condition. Okay, minus 4 Laplace of the first derivative is y sub s minus y sub 0 plus 5 y sub s, and the right hand side Laplace of 0 is just 0. Okay, to solve for y sub s, we're gonna group the y sub s term. Okay, group the y sub s term. Group the y sub s term. That right here, here, and here. Okay, at the same time, we group them. That's meaning we're gonna factor and combine the coefficients. So I have the first coefficient x squared minus 4s plus 5. Okay, at the same time, like I said, we're gonna move a little bit faster. Okay, apply the initial condition y sub 0 equal 1, y prime of 0 also equal 1. So this term is 1. There's also 1. Another 1 right here. Okay, so this turn out we have negative s minus 4 times 1 is plus 4. All right, actually minus 1 first and then plus 4 equals 0. All right, now it's a very basic step. We're gonna solve for y sub s. So y sub s, move everything to the right hand side. I have s and negative 1 plus 4, that is plus 3. Okay, subtract both sides by 3, I have negative 3, and at the same time divided by s squared minus 4s plus 5. Okay, and like I said, we did over here with the characteristic equation with r, right? Now with s, we know that this one is not factorable. Okay, and because it's not factorable, the first thing you're gonna think of is complete square. Okay, recon. Okay, complete square. If I have a sum, okay, a perfect square of a sum, a perfect square of a difference, it turns out to be a squared plus or minus, right, 2ab plus b squared. Okay, so we're going to look at the denominator. Okay, so s minus 3 over s squared minus 4s plus 5. Okay, we want it turned into something look like a squared, right? S squared minus 4s. Okay, instead of writing 4s, I want to have the 2ab, right? I need number 2. I need that number 2, so we're going to write out 2, right, times s times 2 plus 5. Okay, so if you compare term by term of this one, okay, to here, that lie to this, you're gonna see that this is a square minus 2 times a times b, right? Therefore 2 is gonna be b. B is 2. Then all right, so we know that the last term to complete a square is b squared. Therefore we need 2 squared. Can we add 2 squared? We have to subtract 2 squared. Okay, hence this will give us, for the first free term, s squared minus 2s 2 plus 2 squared. The first free term is s minus 2 squared. Okay, how about the last two number? Negative 2 squared plus 5, that is just a negative 4 plus 5, that is plus 1. Okay, then okay, now you're gonna want to ask yourself, for same like example 3, you're gonna ask yourself a question: why do I need to be under this, the denominator to be look like that? Okay, because there are two Laplace transform, e a t cosine b t. Okay, two Laplace transforms that has exactly the same denominator, look like that. All right, another one, there, look, pay attention to the denominator. You see that x they have the same denominator first, and the form is look like this: s minus some number, right, square, that's the perfect square, plus b square. So according to that, if I put one square right there, right, see that, this and that. Okay, so if I want to pull out those two Laplace, two formula, right, I need to do something with this numerator, s minus 3. Okay, so let's take care of them one by one. I'm gonna split them. Okay, so look closely for the s minus a right here. Okay, because A in this case is 2, B is 1. Right. So to get the first formula, to get this first one, the one with the cosine, I need s minus a, which is s minus 2 in this case. Okay. So this one right here, there you go. This one, this box right here. That is just Laplace of at cosine of bt. Right. But because we only have minus 3, right now we write down minus 2. Then what do? To have minus 3, to balance with minus 3, we need minus 1. Okay. So that minus 1, okay, we're going to rewrite that minus 1. We're going to split it. Split this fraction into 2 fractions. Same idea like this. So if I have s, actually a minus b divided by 5. Okay, if I had the same denominator, I can split them out like this: a over 5 minus b over 5. Alright, I'm gonna do something similar to that over here. So what does it mean? It means I'm gonna have the s minus 2 over s minus 2 square plus 1, which is the red box. That at the same time, I'm gonna split that negative 1 minus 1 s minus 2 square plus 1. And why doing that? If you look closely, it actually returns you the sign, the one with the sign, the Laplace with the EAT sine BT. Right, and this is A, that is B, this is B. So turn out that the second box is Laplace of e to power at sine bt. Alright, so now it's laid out perfectly. We just do one last step. It's called inverse Laplace. So actually, let's write like this. So inverse Laplace. Alright, keep in mind, don't write equal. Okay, don't write equal, because they are not equal to each other. You transform them. They are two different functions. They carry similar meaning, but those two functions, they don't equal each other. So inverse Laplace will give me e to power 2t cosine of 1t minus e to power 2t sine of 1t, which is your, and actually which is your solution. Why is it t? Okay, let's factor and clean that up. Box that. There you go. That turned out to be your solution. Okay. Alright. So since we have the solution, how do we know if this solution is true or not, correct or not? If we have these coefficients, these power 2 and this number 1, right, are they actually correct or not? Okay, there's one very quick way to check. Very good way to check. How do I check that? Use the initial condition. Just use the y0, which is 1. Okay, apply y0, which is 1. Okay, so plug in e2 times 0 cosine 0 minus sine 0. This actually 1 times 1 minus 0, which is 1. There you go, check. There you go, you have the correct solution. Alright, so notice something. This is the solution. Therefore, if we solve these problems using the characteristic equation, method, you should also have the same solution like that. So how about we try that? Okay, how about we verify this solution again using the characteristic method? Okay, so we do with characteristic equation that is r squared minus 4r plus 5 equal 0. Because this one is similar to this one. This one is similar to this denominator, s squared minus 4s plus 5, right? It's the same. And earlier we showed that it's non-factorable, not factorable. If not factorable, it's going to give you complex solution. Okay, we established that, right? So if then we're going to use, instead of using the traditional, quadratic formula, see, I already completed the square above. I'm just going to do it one more time over here. So r squared minus 2 times r times 2 plus 5. I need 2 square. I minus 2 square. The first 3 terms will give me r minus 2 square. The last 2 terms is just plus 1 equals 0. Okay, so therefore r minus 2 square equal negative 1. I take a square root. R minus 2 is just plus or minus I. Therefore r is 2 plus or minus I. Okay, because I is 2 plus minus I, therefore the general solution or complementary solution is e to power 2t a cosine of t plus b sine of t. Okay, we are so familiar with this by this time now, right? Okay, then how do I find a and b? Okay, to find a and b, apply the initial condition. So initial condition, right, actually before doing the initial condition, we also need the derivative. Okay, take derivative. We do that anyway, need that anyway. Okay, so derivative is u prime v plus 2 u v prime. Okay, u prime v plus u v prime. Okay, so that my initial condition, first one, y sub 0 equal 1, which is y sub 0 equal 1, which is a equal 1. Okay, we're gonna move because this one verify. We're so familiar with this, so I'm gonna skip on the algebra. Y prime of 0 also equal 1. So if y prime is equal 1, so I have 2 times a plus 1 negative, actually that is would be negative 0, right? Just 0 plus b equal 1, because a is 1, so that is 2 plus b equal 1 for b equal negative 1. So yeah, our solution, okay, a is 1, b negative 1. Therefore, the particular solution, right, is 2. Actually, it's not a particular solution. It's going to be e 2t 1 cosine t minus 1 sine t, which is no more than just e 2t cosine t minus sine t. And is it the same with this one? There you go. Voila. You have the same solution. You're either using Laplace or using characteristic method. But the good thing about Laplace is that you don't have to do the derivative where any step is a little bit more complicated. But you skip on the derivative, you can skip on the integral, right? Jump to the solution. While doing characteristic method the traditional way, you have to do a little bit of derivative. Okay. And still, both of them are very straightforward. Okay. Catch you next example.